Welcome, everybody. Woo! Ready? Yeah, it's nice to hear. Let's get excited. It's really my great pleasure to introduce this year's Radó Lecture by Freedman. Mike got his PhD in Princeton, and he's later a tenure track professor at UC San Diego. He's won a number of awards: Sloan, Guggenheim, MacArthur Fellowships, the National Medal of Science, Field Medal, and for 20 years, he's been working at Microsoft trying to do something really hard and build a couple of quantum computer. And he just joined the faculty at CSNA at Harvard. So let's give all a big welcome to Mike Freedman.
Well, thank you all. It's a real pleasure to be here visiting, and I thank Abner Freedman and Dave Penny for arranging my visit. I'm going to be talking about something very elementary and old school, the Bing involution. So let me, it's kind of a doorway to the topological category. So most manifold topology is about smooth manifolds, but there is some interest in what happens with less regularity when things are a little more shaky, wild. So I'll start with Bing's theorem, then I'll try to explain its context and why it's interesting. So about 70 years ago, R.H. Bing found an involution of S3. So involution, let's just call it I. And all the word involution means is if you square it, it's the identity. So it's a map of order 2. It's a homeomorphism. So that's just a one-to-one continuous map between these compact metric spaces. It happens to reverse orientation, but it's not the usual reflection. So the Bing example has the property, well, let's just use the word, that it's wild. What this means specifically is that for all homeomorphisms of the 3-sphere, if you consider the conjugacy, so you consider the involution that Bing constructed in any coordinates, that's what it means. This is now a coordinate independent thing. For any conjugate of this involution, this is never smooth. So this, in the day when people were studying transformation groups and constructing examples, was a surprise. That's why it became famous in the 1950s. But it turns out that the ideas used in constructing this involution go to the heart of the topological category and were very important for later developments. So this work led to something called manifold factors. I'd say less than 1% of professional mathematicians know what a manifold factor is. Everyone knows what a manifold is. A manifold factor is a topological space, which is not a manifold, but when you cross it with the real line, the result is a manifold. It's quite a surprise, actually, that that's even possible. The double suspension conjecture was another consequence of Bing's ideas. This was work of Bob Edwards and Cannon. And this is now a theorem, it's not a conjecture, and it says that if you take a homology sphere, an integral homology sphere, so for example, if you know the Poincare homology sphere, that's a good one to think of, and you make something of 2 dimensions higher by taking its suspension twice, then this turns out to be homeomorphic to a sphere of 2 higher dimensions. So a homology sphere of dimension n goes to the actual sphere. And the third example was the four-dimensional Poincare conjecture. So the proof of the four-dimensional Poincare conjecture would not have been possible with Bing's methods from 3 dimensions. So I present this as kind of an entree into the topological category, and I'll actually go back to the beginning of the 20th century for its antecedents. But before I do that, I want to state a theorem. And this is the theorem that I proved last year. So 2022, 70 years on from Bing, with my friend and collaborator, Mike Starbird, from Austin, Texas. And the theorem is that, again, Bing's example is not so much a specific example as a conjugacy class. And the theorem is that the Bing involution is very wild indeed. And again, it's for all ways of looking at his involution. So all coordinate systems in which you could study the involution. The continuity, we'll call it the modulus of continuity, is essentially exponential. What does this mean? Well, I told you this lecture was extremely elementary. Whenever you teach a calculus course, you say, for every epsilon, there exists a delta, and you all know the mantra that in order to control distances in the image to epsilon, you have to control the source within delta. So the modulus of continuity is about how small do you have to make delta to get epsilon control. And I like phrasing this in terms of epsilon inverse and delta inverse. And the statement is that delta inverse must be larger than e to the epsilon inverse divided by some polylog factor. For instance, this works. So there's because we weren't quite smart enough, there's a small log correction in the proof. Probably should not be there in the final statement. We'll have an update in 10 years. But basically it says that delta, no matter what coordinates you use to look at this involution of Bing's, it indeed stretches distances tremendously, because in order to control target size within epsilon, you have to make delta exponentially small. If you don't like an inverse up here, by elementary math, we can put it here. But when we wrote the paper, we wanted to think of always epsilon inverse. So I'll put it back. So just for reference, for those who think about analysis occasionally, if delta is like a constant times epsilon, if you can choose it like 100th epsilon, if that works for continuity, this has a name. This is called Lipschitz continuous. And if delta is like a power law, then this is called Holder continuous. So what we show is that the involution in no coordinate system is Lipschitz. It's not Holder. It's much more extravagantly wild. So the original statement of Bing's was focused on the fixed set of the sphere. I said it was an orientation reversing involution. So by theorems of Montgomery from the 40s and early 50s, it was known that the fixed set had to be a topological two-sphere, but the question, just like a mirror reflection, it would have been the two-sphere. But instead of being a too smooth sphere, it's a rather jagged two sphere. And the reflection distorts geometry exponentially. That's what the theorem is. But what I emphasize is you can look at Bing's example of the involution and see this exponential distortion. But his example is not really a specific example. There are many parameters involved. And the question is, was that distortion that you see when you look at the picture essential, or was it an artifact of the coordinates in which you're looking? And the result is that it's essential. Okay, so let's take a step back in history to, let's see, where should we begin? Maybe 1914, the Jordan curve theorem, which actually is from the 19th century, was sharpened to what's called the Schoenflies theorem, which says, I'll state the Schoenflies theorem. I'll state it diagrammatically. It says that if you have the circle, which I write as S1, and you embed it into the plane, so this is the symbol for embed. It means a map, but the little hook means it's one-to-one. So you embed the circle into the plane anyway, it's just we're in the topological category. Then the Schoenflies theorem says that if you think of the circle as the boundary of the two disk, then there's an embedding making the diagram commute. The dotted arrow exists to make this diagram commute. So in other words, what this says is if you take any embedding, even if it looks kind of wiggly, with a circle into the plane, that this embedding is actually the boundary of an embedding of a disk. You can extend the boundary conditions to a one-to-one map of the disk. The Jordan curve theorem said that this circle had an inside and an outside. And this strengthens it by saying, well, the inside is parameterized by a disk. And the best proof of this actually is not Schoenflies, I think, but is Carathéodory's proof. Published in this year, where he gains microscopic control of the Riemann mapping theorem to show that the Riemann mapping, which is can be used to parameterize this simply connected domain, has a continuous extension to the boundary. That was the key. And in order to prove this, he developed an analytic technique, which has been important since then, called extremal length. Now, maybe the next step in this history is 1922. The American topologist Alexander, who you'll hear a lot about, claimed that this same pattern held when you went up one dimension. He made arguments and gave lectures to the extent that you could replace 1 with 2, 2 with 3, and this also with 3. So it's, well, as a professional mathematician, you must have had the experience that you've realized you've spoken too soon. You've talked about something, but you haven't thought about it yet. And Alexander must have had one of these moments, and I think I can explain how he came to this realization. But he realized that this was not right, that the situation was extremely different in one higher dimension, and this embedding did not exist. So he published his revelation actually in 1924 with the apology. And his example I pictured here, and I'll come back to it. So if you look at the larger picture on the right, this is a picture of an embedding of a sphere into 3 space. Now, this little thing up here, that's how you usually think of a sphere embedded in 3 space, and there it is. But let's understand Alexander's embedding. By the way, there are many pictures of Alexander's embedding, and if you look it up on Wikipedia, you may see a different picture that you don't recognize from this one, but all the pictures should be isotopic. So here's a nice round sphere. On the left, I drew kind of a droopy, washed out version of that one, like you've hung it out on a clothesline to dry. But you can kind of see it just sort of sagging, sags and sags and sags. What I've done is I've taken a central cylindrical region, like the tropics, and I've mapped it up here. And then I've taken successive pairs of pants, as we're called in topology. These are a disk with two subdisks removed, called pants for obvious reasons. And these pants can be stacked, and they fill up almost every bit of the two-sphere, except for a limiting Cantor set, which you supply at the bottom. So if you start by understanding the round sphere, which everyone understands, you can easily see this droopy sphere. And then to get to the Alexander horn sphere, all you have to do is at each successive layer, introduce appropriate braidings between pant legs. And that's the limiting object, which is the Alexander horn sphere. And as long as we have the picture in mind, let me point out that it's quite easy to see that the interior region is a 3-ball, because the same correspondence can be made in the interior. But what is striking is that the outside, if you think of this picture as drawn in the 3-sphere, the outside is not a 3-ball, and it's called the Alexander horned ball. So the closed exterior region is, it's a simply connected space, but its interior, the interior of the complement is actually not simply connected. It's quite an interesting space. And I will explain this in detail, but the Bing involution is made by taking 2 copies of the Alexander horn ball and doubling it along the common 2-sphere boundary. So you can go back and forth by reflecting one copy to the other. Maybe I should just step back and make one comment. You know, why were people interested at the turn of the 20th century and even before, why were people interested in wiggly curves in the plane? Why wasn't everyone just satisfied with piecewise linear curves or smooth curves? You know what? Well, from the 19th century, people knew about Kleinian groups, quasi-Fuchsian groups. People who were studying dynamics wanted to know about the limit sets of these groups. And these are very beautiful examples of quasi-Fuchsian groups have limit sets, which are topologically embedded circles, but they're definitely not smooth. The Hausdorff dimension is greater than 1. They are wiggling at every point. They're not topologically wild yet, because a circle in the plane, no matter how it's embedded topologically, always has a product collar on both sides. And this was really the chief question that Alexander was thinking about. He was wondering whether it was true in one higher dimension that if you had a surface just mapped 1-to-1 into Euclidean space or some other manifold, he was wondering whether that surface had a collar structure, whether there was topological product lines. In low dimensions, in circle in the plane, you can construct this product structure by the Riemann mapping using complex analysis. But in 3 dimensions, it just does not exist. If you go back to this picture, in the interior, there's a product collar because the interior is a ball. But from the outside, there's no way of approaching these wild fingers to produce a collar. Okay, so let me just write down what I said in words, that the Bing involution is made by gluing together 2 copies of the Alexander horn ball. So first, just a little bit of abstract nonsense. Suppose you have a reasonable space, maybe a compact metric space, and a subspace. let's just be clear about what we mean by the double of that space. So the double of x along A. All this means is you take two copies of x. So you take x cross, say, 0, 1. And divide out by the relation that A cross 0 is equivalent to A cross 1 for all A and A. So if you have a space X with boundary, quote, boundary A, then we take two copies of X. We could draw the other copy over here, glued together along A. That's a double. If you have a double, you obviously have an involution. So I'll just call I, because you can just interchange the 0 and 1 back and forth. So doubles always have involutions. So the thrust of Bing's theorem is not that there is some space with an involution. It's that the Bing theorem basically can be restated as saying that the double of the Alexander horn ball is not just any old space, but it's homeomorphic to S3. And then using this homeomorphism, you can transport the obvious involution that's taking place on the double into S3. So this is the tricky part. And in order to explain why this is so, well, you need to see why this isomorphism exists in order to see its involution. And that's what I want to show you. And what we'll learn in understanding this isomorphism is a bit of what's called decomposition space theory. So rather than give the definitions of decomposition space theory at the start, let me give the example and then give you the definition. Let me give you some examples and then the definition. So I want to start with the 3 ball and consider a decomposition C, which I'll explain very concretely, which is a collection of closed subsets of the 3 ball, which is designed, this decomposition is designed so that this quotient space is the Alexander horn ball. So what C will be, many things in this neck of the woods, in this area of topology, are defined as infinite intersections. And C will be the intersection of I equals 0 to infinity, what I'll call ordinary CI. And each CI is a solid cylinder, so a D2 cross I, and several copies, so cross the finite set 2 to the I. So I also wrote that here. So this decomposition CI looks like this. C0 is just a solid cylinder, and I've drawn it this way. I could have drawn C0 in another picture just like this, 2-disk cross I. But I have a motive for drawing it like this. But the thing of real interest, which is this guy, the script C, is an intersection. So I have to tell you how C1 sits inside C0, and then I have to tell you how C2 sits inside C1, and so on. And C2 is 2 solid cylinders, so here they are. But the trick is they're going to link each other like this. So what I've drawn is C0 on the outside, and then these two things on the inside are C1. And then within that, there'll be 4 solid cylinders. And that's what I've drawn in this picture. So in order to have room to imagine the construction going on for several steps, I've drawn these solid cylinders to look a bit like cardinal hats, except upside down. But that's just a geometric rendering. And I've color-coded it. So the black thing is C0, the blue thing is C1, and the red thing that has 4 components is C2. And then there's a little bit of hint of green there, but it's getting kind of hard. Now, the assertion that I want you to follow along and agree with, maybe we'll take a vote in a minute, is that I want you to see that when you divide out C, the infinite intersection, to points, you get the Alexander horn ball. So first, I think I need to say what dividing out means. So this thing C has a lot of different components. This nested, this dyadic nesting leads actually to a Cantor set of components in the limit. And if you draw them in a nice monotone way, as I'm doing with that cardinal hat, each individual component of intersection, connected component, has the topology of an arc. So you have a Cantor set worth of arcs. It's a Cantor set cross an arc is what script C is, but it's not a product, it's a subset. And the fact that all these braidings are happening of these C's as you go down, this linking or braiding produces an interesting embedding or map from Cantor set of arcs into the ball. And what the quotient means, it's the quotient space where those components are called points with the strongest possible topology. Strongest possible topology, making the quotient map continuous. Remember, continuous means inverse image of open sets are open. As topologies become stronger, you add more open sets. So the definition of quotient topology is just the strongest topology, making the quotient map continuous. It's the natural thing. Now, this is something that we really need to see, and that's why I made these 2 pictures in advance. So I want to think of crushing these script C to points, the components of script C to points, as a sequence of smooth processes, which I think of as like a vacuum sucking a nice ordinary tame sphere, which you can think of as a half space, sucking them down and down and down. So what you should think of is that this wild sphere, the Alexander horn sphere, is going to be produced before your eyes, like a magic trick, by evacuating air, if you like, from the successive stages of these solid cylinders. So as you suck air out of the black solid cylinder, 2 proboscis descend from the plane. It sucks the plane down, and then you start sucking air out of the blue ones, and that produces feelers on the subsidiary feelers on the 2 original feelers. And those subsidiary feelers are linked, as I drew here. So as you keep sucking and sucking and sucking, the smooth plane is, the word is pseudo-isotopy is sometimes used. It's a smooth isotopy until the very last instant when it loses its smoothness. And in this isotopy, these tendrils or feelers are successively drawn out and linked with each other. And as you're doing this, the arcs of script C are getting smaller and smaller and smaller. And when they reach points at the last stage, the only points that have been moved infinitely often in this process are the infinite intersection of all those solid cylinders. Everything else just moves for a while and stops. So so it takes writing down some epsilons and deltas to prove this, but this is the conception. As you do this pseudoisotopy, you simultaneously crush script C to points, a Cantor set worth of points, and take the nice smooth sphere and draw out these linked horns to get the Alexander horn sphere. So that's the proof sketch. Should we take a vote? Raise your hand if you understood it. That's not bad. Raise your hand if you disagree. You understood that it's obviously wrong. Okay, well, okay, so plausible. Okay, now I want to show you a little bit of brilliance, a little bit of Bing's brilliance, because he was a very homespun, good old boy Texan, really, and he would never have admitted to thinking functorially or anything like that, but he was, because here's basically what he reasoned. He reasoned that the three sphere is the double of the three ball along the two sphere. If you double three ball, you get a two sphere. That's sort of fact one. Fact two is the one I put in orange here, that the Alexander horn ball is this quotient. Now, if you take the double of the Alexander horn ball, so this is now fact three, this should be the double of the ordinary ball. I'll leave out the sphere that you're doubling along from the notation, divided out by the double of C, which notationally I'll call D. And what does D look like? I didn't draw a picture of it in advance, but C, well, let me draw D and then see if you agree, if it looks right to you. Okay, now this gets exponentially time-consuming to draw, so you're going to have to sort of go with the flow a little bit. But what I've drawn here, before I mess up the picture, is inside a solid torus, I put two solid tori, which are sometimes called a Bing pair, in honor of Bing. It's a way of embedding a pair of solid tori inside another one. They're both degree 0, but they're not trivial. They have a way of grabbing each other. And imagine that I iterate this forever, that inside this next one I put in a Bing pair in orange, and inside this other one I put in another Bing pair in orange. And then with some other color I put 8 and keep going like that. Then notice that this picture has a reflection symmetry in the middle. It's made by some picture on the right and its mirror image on the left, so it's a double of the picture on the right. But notice that is the picture that I drew here. So the idea is that the three sphere, so this gives, yeah, let me just finish the equality here. The double of B3 is S3, as we already noted, modulo D. So if I call the infinite intersection here, say the infinite intersection I equals 0 to infinity of the doubles of the CI, if I call that by definition script D, that's the Bing decomposition. then I haven't proved that the double of the Alexander horn ball is the sphere, but I've related it to the sphere. I've said it's the sphere, it's a quotient space of the sphere where I've crushed the components of D to a point. So that's just functoriality. But the genius of Bing is to see that this the quotient of the infinite, by the infinite components of the infinite intersection is actually the sphere. And in order to do this, he developed something called the Bing shrinking criteria, which I'll tell you about. So this is the Bing shrinking criteria. And you can state it this way: if you have a map from one compact metric space to another, which is onto, that's the double arrow, and it has the property, so call this map pi, such that for every epsilon, there exists a homeomorphism, h sub epsilon from the source to itself, with two properties. One, the sup norm distance between the original projection pi and h epsilon followed by pi is less than epsilon. And two, the diameter in the usual metric of the sphere of h epsilon of pi inverse of any point y is less than epsilon for all y. Given this, then pi is what's called approximable by homeomorphisms. Approximable by homeo. So this is called the Bing shrinking criteria because of this condition 2. The self-homeomorphisms of the source make the preimages, which are these long arcs, small. And the condition 1 is that the homeomorphisms that do this are not random, but they're somehow coherent. They don't move things much in the quotient space, which is to say that when you're working on very deep stages, you don't have to disturb the outer stages. You can always work near the limit. And this can be proved by smart undergraduates given a few pointers. It's just epsilon and delta, first year topology kind of stuff. But it's beautiful, it's a beautiful result. But in order to apply it to our situation, the reason I say brilliance is we have to think of a way, we have to find these h sub epsilons. We have to think of a way of shrinking the components. And I want to compare this actually to what's called Antoine. I was forgetting the name. Antoine's necklace. So Antoine's necklace actually is another example that dates from 1914, French mathematician Antoine. And it's a certain subset of 3 space. Maybe it deserves a larger picture than crowding into here. So let me put it here. So Antoine's necklace is a Cantor set in 3 space, which is defined as an infinite intersection of solid tori according to the following pattern. We take a big solid torus on the outside and we make a chain of, say, 3, often it's drawn with 4, but 3 is enough. you take a chain of 3 solid tori inside, just a daisy chain like this. And then within each of these, do the same thing. I'm getting a little repetitious, but that's the nature of this subject. You always, if you like what you did, you just keep doing it. I'll try not to make any lurid jokes about that. Now, notice that the geometry is such that the diameter of these components is going to 0 as a geometric series. So without any work at all, without thinking of shrinking homeomorphisms, this thing is sort of self-shrinking. The limit of the infinite intersection is already a Cantor set. So nothing has to be done. But the astonishing thing is here, where it's not self-shrinking, you can come up with the little twists and tweaks that make it shrink. So the case of 3, 4 and 3 and 5, 3 and higher are all the same. These things just shrink. And 1 will not shrink if you embed one solid torus in another according to this pattern, which is called the Whitehead double, and you keep iterating that. There's no way to shrink this. But it turns out 2 morally is on the Antoine necklace side. And the reason I wanted to show you this example is some evidence from the literature of the time suggests that it was thinking about Antoine's necklace that led Alexander to realize his mistake. He was probably thinking about trying to put in a disk with boundary this circle that didn't cross the necklace, and he's starting to make horns on the disk. And I think that probably that example led him to the Alexander horn sphere. Okay, so in order to maybe to appreciate Bing's shrink of this, I just have to tell you, it's sort of irresistible to tell you a little bit about Bing. So he was born in Oakwood, Texas in 1915 and was a football coach and math teacher at his high school. He was drafted into World War II. And after the war, he went back to his job. But the state of Texas, its legislature, being very liberal and forward-thinking, passed a law that any high school teacher who got a master's degree could earn an extra $400 a year at the expense of the state. And Bing thought this was a good idea, so he enrolled at University of Texas and became a student of R.L. Moore's. He had to take some elective, and that was topology. And he got involved in this program where you're not told anything. You just have to figure everything out yourself from a set of hints. And he thrived in that environment. And one thing led to another. He became a faculty member there and a member of the National Academy of Sciences. And I knew him in his later days, and yeah, he was a great guy. Yeah, he was at Wisconsin, but he came back to Texas. When I knew him, he had returned to Texas. Okay, so how in the heck do you shrink this thing? That's going to be the most exciting moment here. So what Bing realized is that this was essentially a one-dimensional problem. If you take you can sort of squeeze the torus as thin as you like, epsilon, in all but one direction. And then successive tori, stages inside, it's sufficient to measure whether they're shrinking or not, just with respect to some discrete set of planes. So let's put 100 planes vertically like this, equally spaced, and measure the length by how many are crossed by a given torus, just a discrete measurement like that. And what he realized is that if this is your starting torus, if the tori inside are rotated so that one of them misses the rightmost plane and the other misses the leftmost plane, but they still link as they need to, he realized that this was good progress. because you can iterate this. Inside, say, the orange one, you can now play the same game. This one, the orange one crossed, instead of 3, it crosses 2 planes, but you can arrange that the tori inside it you can arrange their turnaround points there, here, like you. So one of them goes like this. And the other one goes, sorry, to make this convincing, let me draw the original orange one larger. Okay, so the turnaround points can be inside the orange torus, can be like this and like this. Does that make sense? So this one goes like this, and this one goes like this. And each of them only cross 1 plane now. So I started with 3 instead of 300, but the same thing works. Okay, so now this actually fits the Bing shrinking criteria because you can choose epsilon in advance. But there's still something intellectually puzzling because after you get down to this scale, it's not clear how to proceed. And I asked Bing if that worried him when I met him. And he said, well, first he gave me the mathematical reason he wasn't worried. He said, well, you replace this family of original planes with much finer quote planes, which are just little tick marks along the last achieved stage. And you put in, instead of 300 of these, you put in 3 billion of these tick marks. And then you start playing the same game with respect to these tick marks. And for the longest time, you make no improvement on diameter. But finally, when you get down to 1 or 2 tick marks, you've made something very small. And then you start again with 3 trillion tick marks. You keep doing that. Actually, he had a very colorful way of explaining it. He said when you're in a gym and you're climbing a rope, it does you grab the rope and you pull down. He says it does you no good at all just to keep pulling. You have to let go with one hand and get a new grip. So that's the new grip, these tick marks. Okay, well, so what are the main points left? This is the end of the proof that there is a Bing involution, because by the shrinking criteria, you can now see that when you divide out this decomposition, this space, the doubled space with the involution, is the 3-sphere. They wouldn't be complete without trying to draw a sketch of the fixed set. And the sketch of the fixed set is not so hard to understand now that you understand the shrinking. Because imagine this plane of symmetry before you do the shrinking. That's the fixed set of the smooth involution on the 3-sphere. In order to see Bing's fixed set, all you have to do is follow the distortion of the plane as you rotate these solid tori inside and they drag the plane along. So what happens is the plane starts to get these pseudopods because of the dragging, because of this sliding of the subrings back and forth. It'll get some pseudopods sticking one way and then another one another. And at the next stage, this will have some piece that sticks out and some piece that goes back. And these various pieces from different stages will start to hook around each other in complicated ways. And that's the fixed set. And once you kind of see the picture of the fixed set, you can understand the proof that Mike and I worked on. I should say, not only did this proof come 70 years after Bing's theorem, but Mike and I actually worked on this for 40 years. We started this project in 1982. We didn't work every day on it, but But the whole idea of the proof is to somehow look at these fingers and realize that you can make estimates that this Bing shrinking idea is essentially as fast as you can shrink it. There's no faster way. So you have to quantify that. And what that means is that at the nth step of the proof, these fingers, I call them pseudopods, these fingers are length order 1 over n. You really can't do better than that. But because of the exponential nature of the construction, the area of the cross-section, if you take like a geometric plane and you cut off one of these fingers, this geometric cross-section will contain 2 to the n many different fingers from all these different solid tori. So the area has to be like 1 over 2 to the n. But if you have a little cutoff area that's very small, exponentially small, but the fixed set is harmonically long, then when you look at points in the geometric plane that you use to cut off, points that are exponentially close to the boundary will have to stretch out over this finger, because remember, it's an involution with this as the fixed set. So this geometric disk is on the left of the fixed set. Its image under the involution will be to the right of the fixed set, so it'll have to go around. There'll be points exponentially close to the boundary, which is fixed, which end up at the tip of the bag. And that's sort of, that's the goal. We call this A-D stretching, A for area and D for distance. Of course, the reason the proof is 50 pages long is you're not trying to prove stretching for a particular picture, which has particular coordinates. You're trying to find some coordinate independent measures of all these things. Maybe just a couple final comments about, there's a generalization. I don't know if I even can spell this word. Let's give it a try. Is that a word? Skolem? Oh, good. Okay. Spelling is not my strong. So this is a corollary of a proof, right? Well, there's a lovely skolem to the proof, which is, I'll just state it. You give me any growth function, reals to the reals, no matter how rapid, like Ackermann's function or whatever you want to make up. I can produce an involution on the 3-sphere whose modulus of continuity in any coordinate system grows faster than that growth function. So you can do much more violence than exponential. And it's very simple. The idea is that Bing's example is based on Bing doubling, where in each solid torus we put in 1 Bing pair. But there's no reason why we couldn't put in 2 Bing pairs at each time, or 1,000 Bing pairs at each time, or at the nth stage, Ackermann many Bing pairs at each time. So by putting these outrageously growing functions of number of Bing pairs, we can force that area estimate to go down as fast as we like. We have complete control of that. So then this analysis of area versus length gives an arbitrary amount of growth. And maybe one last, just couple concluding remarks is, you might wonder why dimension 3? Well, nothing like this can happen in dimension 2 because all finite group actions on surfaces are conjugate to smooth actions. So you need at least dimension 3 to talk about wild group actions. And it turns out that in dimension 4 and higher, they're very easy examples of non-smooth involutions, which are Lipschitz. So there's no gap. In dimension 3, my conjecture is, we haven't proved this, but I think I'm quite sure it's true. My conjecture is that any group action on any topological group action on a manifold can be made smooth in a suitable coordinate system unless one of the elements of the group acts with an exponential Mach. And that's only true in dimension 3, because we can construct examples in all dimensions higher, which are only mildly stretchy, Lipschitz, which are wild. Yeah, maybe that's a good place to pause, and I'll take any questions. Yeah.
So this is square equal to identity. What if you look at two groups?
Oh yeah, yeah. Well, yeah. So all these examples have generalizations. Of course, as soon as you go away from order 2, you lose this two-dimensional fixed point set. By the way, the Bing double picture, which we've been drawing, has another symmetry, which I haven't emphasized. I've emphasized its reflectional symmetry, but this picture also has a Z2 rotational symmetry around this axis, like it was a pig on a barbecue or something. So even with this example, there's another Z2, and I believe that this also has exponential Mach, though the proof technique has to be generalized considerably. So in our paper, in an appendix, we give some suggestions to the interested reader how to try to prove this, but we haven't. But my conjecture is that all finite order group actions are amenable to a similar analysis in dimension 3.
Let's thank Mike again.
And thank you guys.